All right, so assignment 4.3. This is the second derivative test, also connected to concavity and point of inflection. So let's go through the assignment of that together, where you might need support or not. So write down the title, put your name and date on it. Number 1 says, use the appearance of these graphs to answer these questions. So I'm going to show you the graphs I have. In part A, interval in which the graph is concave up, interval where it's concave down, and what are the points of inflection. So let's look at that. So if I bring this over for number 1, concave up means it smiles, concave down means it frowns. And so what interval do we have? So first of all, follow the first part of the graph is smiling. So from negative infinity all the way to what x value, and when you look at it, you're going to approximate it, but I think it's obvious that this x value, it stops smiling and then it frowns. So first of all, what interval is it smiling, concave up? So that would be from negative infinity to positive 1. On here. B, where is it concave down? Well, from positive 1, and then the entire graph left is frowning. It never changes. So from positive 1 to infinity, it is concave down. And then part C, where are the points of inflection? Is there a point where the concavity changes? And so there is one point of inflection. It asks for the point. And at 1, 0, we have a point of inflection, because it changed at that point from concave up to concave down. And that's the definition of point of inflection. 2. Where is it concave up and where is it concave down? So let's look first. This, what is it doing? And if I continue this and had an understanding, it's frowning. It's curving downwards. So it's concave down. The only part that's concave up is in the middle. And where does it go from? From negative 2 to positive 2. So from negative 2 to positive 2, there we go, maybe. So from negative 2 to positive 2, it's concave up. How about the sides here? So this is negative infinity to negative 2. That's concave down. And the other side's also concave down from 2 to infinity. So concave up is smiling, concave down is frowning, and it can be part of a frown, not a whole frown. This is a full smile. Part C, is there a point of inflection? Is there a point where it changes? And there is no point of inflection. So the concavity changes at an asymptote rather than at a point. 3. Move my camera around here. There's 3 and 3. See if I fold this up a bit. So when it's off a graph, it makes it different than if it's more algebraic. So there's 3. So for 3, where is it concave up and where is it concave down? So follow it. So smile, and then at what point does it stop smiling? So concave up from negative infinity to the x coordinate there, which is negative 1. Notice it then frowns. So there's a little frown and then a smile. So what's that little smile? It goes from 0 to 1. You have a little smile, and that's it. For concave down, that negative 1 to 0 is a frown. And from positive 1 to infinity, it frowns. So those are the intervals of concave up and down. So up, down, up, down. There it is. And then at what point does it change concavity? So it changes concavity at negative 1 and negative 1. It changes concavity at 0, 0. And at what other point does the concavity change? Is at 1 and 1. Just double checking to make sure I'm doing it correctly with you, which I am, of course. Number 4. I'll switch it around like this. So there's number 3. Number 4, let's talk about it. So concavity-wise, this starts, now for this one it doesn't go to negative infinity because there's no arrow at the end. So the x-coordinate is -2. So from -2, it's concave up to what x-coordinate? 1. Sorry, that's A. That's a line. A line has no concavity, so no concavity. Here, it's concave up from 4 to 6. And here, it's concave up from 8 to 9. So can you identify the spots where it is smiling? Next, part B. Where's it concave down? So up, a line, up. So there's one part where it's concave down. That's from 6 to 8. And that's it. Again, remember the slanted line has no concavity, so it's not concave up or down. Point C, what are the points where it changes concavity? So I want you to notice that it's concave up and then a line. So the concavity, it went from up to no concavity. It has to change concavity, either concave up to down or vice versa, and the derivative has to exist at that point. So neither is true here. This is not a point of inflection because it goes from concave up to a line. So it has to change concavity. So on the other side, it still needs to have concavity. Same thing here. The concavity doesn't change. It goes from a line to a curve, so no concavity change. Here, at 6,1, you can see concavity. So it smiles and then frowns, and the derivative exists there. So the point of inflection is at 6,1. Here, it frowns and then smiles, so the concavity changes. But the problem with this one is the derivative doesn't exist there because it's a cusp. So when you look at that sharp corner, the derivative does not exist. It's undefined. And because the derivative is undefined, there's not a point of inflection there, even though the concavity changes. So the only one that meets the criteria is at 6 and 1. The concavity changes and the derivative exists. All right, number 5. All right, I'm going to move my camera just a little bit so I don't need to look off the graphs anymore. So here's number 5. So in number 5 it says, show organized steps and a second derivative number line to show the same 3 questions for these functions. Okay, so now we're not looking off a graph, but we're doing it algebraically. Can you tell me concavity? So it's the second derivative test. Now for the second derivative, we have to find the first derivative first. So the first derivative here is 4x cubed subtract 12x squared when you multiply, and then 0. And now the second derivative is 12x squared minus 24x. So there you start. There's nothing that makes this undefined, so we're going to make it equal to 0. And then when I do that, I'm going to solve by factoring. So I'm going to factor out a 12x. And then I get the answer is 0 and 2. So now I'm going to draw a number line for 0 and 2. Now it's a second derivative number line. Those are your critical numbers for the second derivative. There we go. So 0 and 2. So now on that second derivative number line, I've created 3 intervals. You pick any number you want in the interval. So any number smaller than 0, and just see if the answer is positive or negative. So if I pick -1, it's a negative times a negative, which is positive. So what I found was from negative infinity to 0, it's concave up. 0 to 2, pick 1, positive times a negative. So from 0 to 2, it's concave down. And then the last one, pick any number bigger than 2, plug it in, you can see the answer is going to be positive. So part A says, where's it concave up? So it's concave up from negative infinity to 0 and 2 to infinity. So when the second derivative is positive, it's concave up. Part B, where is it concave down? From 0 to 2. And then C, where the point of inflection. So where did it change concavity? So at 0, and it changed at 2. So it has 2 points of inflection. How do I find the y-coordinate that then goes with 0 and 2, knowing it changed? Is I go back to the very beginning and plug it in way, way, way at the beginning. So if I plug it in way at the beginning, if I plug in 0, I get the answer 2. This one's more complicated. Plug in 2, you get 16, subtract 32, that's negative 16 plus 2, I get negative 14. Let's see if that's true. It is. So to find the y-coordinate, you have to go back to the beginning, to the function, not the derivative, to find the y-coordinate that goes with it. These are points of inflection because the concavity changes at those x values. Number 6. So for number 6, the function is 3x to the 5th, subtract 5x to the 4th. I need the first derivative. I need the second derivative. And then I make it equal to 0. There's nothing that makes it undefined to worry about. So I'm going to factor out a 60x squared and be left with x minus 1. When you solve it, 60x squared equal to 0, that just gives you the answer 0. So 0 is an answer. And positive 1, draw a number line for that. So pick any number between less than 0, so any negative number. So you plug in a negative number and it's positive. Plug in a negative number, it's negative. So a positive times a negative is negative. Plug in a number between 0 and 1, like 1/2. So 1/2 is positive. 1/2 take away 1 is negative. So a positive times a negative is negative. And then plug in a number bigger than 1, any number bigger than 1, and it's positive. So we just found concavity. So part A, where is it concave up? From 1 to infinity. Where is it concave down? And you could actually just write this as one big interval. So because the concavity didn't change, you can just go negative infinity all the way to 1. Part C, where are the points of inflection? Well, point of inflection only happens when the concavity changes. So not at 0, so when it's 1, and then where do I go to find the y-coordinate to the function? Plug in 1, and it's 3 take away 5, so at 1, negative 2 is the point of inflection. 7. So here's a function, not a polynomial. So how do I find concavity, second derivative, and so on? Take the first derivative, that's 2/3 x, subtract 2, subtract 3, that's negative 1/3. The derivative of negative 3 is 0. I need the next derivative. So again, multiply a negative times a positive. Just multiply the tops and bottoms. That's negative 2 over 9. Subtract, negative 1, subtract 3, that's negative 4/3. And that's what you're looking at. So I'm going to make it equal to 0 and solve it. So since now we're doing algebra, I'm going to write this a little differently. So I'm going to go negative 2, 9, x to the 4/3. So if I put it where it belongs, it becomes a positive exponent, equal to 0. And I want you to notice in this case, look at the numerator. It's impossible for this to equal 0. So 0 divided by something, but there's no variable here. So even if I cross or multiply both sides, the variable will be done. There is nothing here that would make it equal to 0. So let me just double check my answer key. So the only thing to look at here then is there something that would make it undefined. So second derivative, what x value would make this undefined? And it's 0. So that's the only one to look at because it makes it undefined. There's nothing that makes it equal to 0. If I plug in a negative number, just recognize the cube root of a negative. The cube root of a negative is negative, but if you go to the 4th, it becomes positive. So if you put in a positive number, This 4 makes it positive. A negative number, the even exponent makes it positive. No matter what, the denominator is always positive. So a negative divided by a positive, whether you put a positive number in or a negative, will always give you a negative answer. So what we learned was there's nothing that's concave up. It's all concave down. And there's no point of inflection. So there's no concavity change, let alone in terms of a point there. All right, number 8. Use the second derivative test to find the relative extrema points. So let's do that. So the concept of using the second derivative test is, if you have a critical value and you know it's either a maximum or a minimum, if you do the second derivative test, something that's concave down creates a maximum. Down creates a max. If it was concave up, it creates a minimum. It's a little bit counterintuitive unless you draw it. So concave down creates a maximum. Concave up creates a minimum. So just be aware that when it's negative right here, so negative or positive, negative concave down, maximum, positive concavity, minimum. So we'll practice that. Just takes a moment to think and practice it. So we have x cubed subtract 3x squared plus 6. So step 1 is to take the first derivative. Now we're finding the critical numbers for the first derivative. The extreme points are first derivative, not concavity. But the second derivative test, we test those points with the second derivative. So first derivative, 3x squared minus 6x, make it equal to 0. Solve it by factoring. So factor out a 3x and then solve it. So the two answers are 0 and positive 2. Those are the critical values. So when you take the second derivative, it's 6x minus 6. So when I plug in 0 here, 0 gives me a negative answer. When I plug in 2, it gives me a positive answer, because 12 take away 6 is 6. So what does that tell me? So at 0, it's concave down, because the second derivative is negative. So at 0 is a maximum. So we have a relative max at 0, and if I want to find the y-coordinate, go back to the function, plug in 0. So at 0, 6 is a maximum using the second derivative test. The other one's a minimum. So a positive concavity, so it gives you a positive answer, means there's a minimum at 2. So if there's a minimum at 2, go back here for that. So 2 cubed, 8. Squared 4, negative 3, so it's 8 to take away 12, negative 4 plus 6, I think it's 2. So I think it's 2, 2, like a ballerina. Just confirm. Yep. So that's the minimum of it. So there's a second way to find a maximum and minimum rather than doing a number line. So if you don't want to do a first derivative number line, plug it into the second derivative and it will give you the answer. Number 9. Same thing. So number 9 is f at x equals negative a quarter, x to the 4th, plus 9 halves, x squared, plus 5. So we're going to take the first derivative. That's 4 times a quarter, so that's negative 1x, subtract 1 to the exponent. 2 times this, that leaves you with 9x, and then the derivative of 5 is 0. Now we're going to make that equal to 0 and solve it. So factor out and negative x would be easier. So factor out a negative x and you get x squared minus 9. Then that's a difference of squares. So if you fully factor it out, that's what it looks like. So I get 0, positive, and negative 3. Those are my critical numbers. Then I find the second derivative. So if I'm finding the second derivative, take the derivative of the first one. That's negative 3x squared. And then 9x is 9. Now I'm not making that equal to 0. I'm going to take each answer and see if it's concave up or down. So plug in 0 and you get positive 9. That's concave up. That means it's a minimum. And the minimum then, the relative minimum, you plug 0 back in here and you get the answer 5. For the next one, which is what, 3? So if I plug in positive 3 into the second derivative, you get a negative answer. And I don't actually care what the actual negative number is. I'll figure it out for you. Negative 27 and 9, negative 18. What I care about is that the answer is negative. That means it's concave down, so that is a relative maximum. So at 3 is a relative maximum. Now you'd have to plug 3 back into here to find the y-coordinate. I'm just going to do it for you. So that's 101 over 4. I'm sure you could do that if you had to. Then the second derivative at negative 3, what does that give you? Well, negative 3 squared, it's going to give you the same answer. And that means it's also a relative maximum because it's concave down. And if you plug negative 3 back into here, you actually get the exact same answer, which is 101 over 4. It's an even function. So that's the second derivative test to see where the turning points are. Number 10. For these problems, find the x values of the minimum points and the x values of the maximum points. So it says that negative 3, 1, and 3 are critical numbers. Then it says the second derivative at negative 3 equals negative 2. That means it's concave down. That means it's a relative maximum at x equals negative 3 because negative 3 is a critical number. That's how that connects. The second derivative at 1 equals 0, so no max or minimum. That means because there's no concavity there, it could be a point of inflection, but it can't be a max or min, so it has to be a positive answer or a negative answer. And then the last one at 3, it's positive 2. Positive 2 means concave up, which means a minimum. So we have a relative minimum at x equals 3. Now we're not given enough information to find the point, the y-coordinate that goes with it. Number 11. So for number 11, I'm going to just write the information down. F prime at negative 2, F prime at 0, F prime at 4. So what it's saying is that these are all critical numbers because the derivative at those numbers give you the answer 0. So negative 2, 0, and 4 are critical numbers. And why are they critical? Because the first derivative, when you plug it in, gives you the answer 0. That's the definition of a critical number. And then it gives you a second derivative number line with negative 1 and 2. Now negative 1 and 2 are not matching, and they shouldn't match because this is a second derivative in the critical numbers. So for the first derivative, negative 2, what interval is it in? It's here, and because it's concave up there, so there's a relative, so concave up means a relative minimum at x equals negative 2 based on the information. Concave up. 0 on the next interval, that's concave down, so that means it's a relative max. If it's concave down, that's at x equals 0. And then where's 4? So it's concave up again. So at concave up, there's another relative at not just negative 2, but also at 4. So I'll just add it to that. So it's concave up in those intervals. So concavity can tell us where the maximums and minimums are. All right, number 12. Without using a calculator, find the max and mins and points of inflection, then sketch a graph. It is not necessary to find the x-intercepts and so on. So let's do that together. Analyzing and graphing, big question. Can you use calculus tools to graph? Here we go. So step 1, I'm going to take the first derivative. That is 6x squared minus 6x minus 12. There's nothing that makes it undefined. Make it equal to 0. I'm going to divide out the 6. So if I divide everything by 6, that would give me x squared minus 1x minus 2 So I divided everything by 6. Factor it. So my two critical numbers are 2 and -1 for turning points. Now I'm going to need my second derivative anyway, so might as well just use it. So the second derivative gives me concavity. That's going to be 12x minus 6 equal to 0. Add 6, divide by 12, you get 1/2. So what's going to happen here? If I plug 2 into the second derivative, I get a positive answer. So that is concave up, means that's a minimum. If I plug -1 into here, you get a negative and another negative, you get concave down. So at -1 is a relative maximum. And we'll find the y coordinate that goes with it in a moment. So we found here and here the relative minimum and maximum on our graph. Now, where would I go to find the y coordinate? Oops, I went too far. Is you would plug the 2 back into here. I'm going to do it for you just to save yourself the headache. If you plug positive 2 in, you get -15. Again, plug it back into the function. If you plug -1 into here and simplify it, you get 12. So you can try that with the calculator or even by hand if you want to. It says no calculator. So I just did the little headache for you. There's the minimum and there's the maximum. Now, concavity. So we're going to see if that's true or not. At 1/2, do we have a point of inflection? If you plug in a number smaller than 1/2, like 0, you get a negative answer. If you plug in any number bigger than 1/2, it's positive. So at 1/2, we have a point of inflection. So we'd plug 1/2 into here, and again, I'm going to give you the good news, the y coordinate there. So for 1/2, you get the answer -3/2. So you don't have to, it's not that kind of thing. I just want you to go through the calculus thing and not get a headache over just plugging in and getting an answer. There's one more thing that'll be helpful. So we're going to sketch it right here. So let's plot the points and just sketch what we have. So we have like 2 and -15. So 2 and -15, I'm just sketching. So just be nice to yourself. And then -1 and 12. So we have -1 and 12. We have 2 and -15, and then at 1/2 and -1.5, so like right in there. Just estimate where that is. Okay, 1/2 and -1.5. And then what's else I was going to say what's going to be helpful is to know the end behavior. So what's the power term here? This is like from 100 years ago. The power term is the term with the biggest exponent, and it's positive with an odd exponent. So if it's positive with an odd exponent, the right end goes up and the left end goes down. That's going to be helpful, just that. The right end goes up, left end goes down. So let's do that here. So don't worry about the intercept, so just sketch it. So I know the right end goes up. I'm going to follow. Now notice that this is concave up. So concave up all the way to this point, because that's the point of inflection. So concave up, it smiles, and then after here we're going to connect. Know that technically 5 is the y-intercept, so somewhere around there. And it turns, and then it's concave down the whole way. So at this point it goes from concave up to concave down. And there's a sketch using calculus tools to know how to sketch a polynomial. Last year you could not find the turning points. You'd have to use Desmos. Now I taught you how to find the turning points without a calculator. Feel the power. Okay. 13. Same thing. We're going to take the first derivative, make it equal to 0. We're going to factor this. So there's a 4x squared. That leaves me with 3 minus 1x. So if I solve them, if I take 4x squared equal to 0, it's 0. Here, the answer is 3. That makes it 0. Oh yeah, I wasn't going to do that, right? In terms of increasing and decreasing too. It's fine. Let's do it. I didn't do it last time, so let's do it here. Where is it increasing and decreasing? Plug in a negative number. A negative times a negative is positive, and that will be positive. Plug in positive 1, it's positive. Plug in any number bigger than 3, and you get negative times a positive, which is negative. So it's positive, positive, negative. So it increases. And then this right here could be a point of inflection. We're going to find out. Not maximum or minimum. So here we found out that at 3, if it rises and then falls, is a maximum. So we have a maximum at positive 3. And then I would plug it back into here to find the y coordinate. So if you do that, you get the answer 27. So at 3, 27. So I plug 3 back into the function to get the y coordinate. That's a maximum. Now the second derivative, that would be 24x minus 12x squared equal to 0. Factor out at 12x, that's 2 minus x. Again, solve it. 12x gives you the answer 0. That's positive 2, because 2 take away 2 is 0. And then a number line from 0 to 2. Plug in any negative number. That'd be a negative times a positive, which is negative. Between 0 and 2 is 1. So plug in positive 1, and you get a positive answer. And any number bigger than 2, like 4, will give you a negative times a positive, which is negative. So negative, positive, negative. So this tells you the concavity of our graph. So do you see at 0, the concavity changes. So plug 0 back in here and you get the answer 0. That's a point of inflection. Also at 2 is a point of inflection. That changed there too. So if I plug 2 back in here, I get the answer 16. Just saving you. So we have 2 points of inflection. We have a maximum and increasing and decreasing. So now let's take this information. Also recognize the power term is negative x to the 4th, not 4x cubed. What term has the biggest exponent? So because of that, both ends are going down. So the end behavior is both ends going down when I sketch it. All right, let's put it together. So 3 and 27. Let's pretend. There's 27. 2 and 16. Pretend. There's 16. We're sketching it. 0, 0. And that's it. So those are the key points. The intercepts will just crosses where it crosses. We know both ends go down. So first of all, this is concave down up to 2. So I'm going to go concave down up to 2. So there it is right there. So I know the right end goes down, and I know it's concave down through those points. I also know, and this is going to fit like a puzzle, that from 3 on it decreases, but to the left, so it goes increasing and then decreasing. So from 3 on, but the rest is all going to be increasing. What happens at 0 is another point of inflection. So the concavity changed. So it's no longer frowning, it's now smiling. So can you do a little smile? And then after it smiles, it changes concavity, and then it frowns again. So it has a little cute little curve in there. So concave down, concave up, concave down. So it follows the second derivative. Down, up, down. It increases all the way to 3. So notice it increases all the way to 3, and then it decreases. So ignore this arrow. It goes up, and then it comes down. And we have the key points. There's your point of inflection, your maximum, and there is no minimum. There's only one turning point at 3 and 27. 14. Powerful, isn't it? No calculator. Use the following information to sketch a possible graph of f. If f is a continuous function, so no breaks or jumps or anything like that. So we're given f at -1 equals 3. That's a point on my graph. We're given f at 2 equals 0. That's a point on my graph. we're given the derivative, f at negative 2 equals negative 1. There's another point on my graph. All those need to be on my graph. And then the derivative at 2 does not exist. So the point exists, but the derivative. So there's a cusp or corner at 2 that makes the derivative doesn't exist. We have a number line for the first derivative. So it increases, decreases, increases. The second derivative, concavity, it is concave up, concave down, and then concave down. So as we do this, we're going to look at both at the same time and understand how to draw something. If it's increasing concave up or increasing concave down, we need to know how to draw both. Okay, let's sketch this. So those are the x values at negative 1, at 2, at negative 2 that we care about. Points we know. We know negative 1 and 3. We know 2 and 0, and negative 2 and negative 1. So the derivative doesn't exist, but the point exists there. So let's start there. So to begin with, on the left, we'll go left first. To the left of negative 2, it is concave up. So to the left of it's concave up, and it's increasing. So concave up and increasing. Make sure I got this right. Concave up and increasing. So it smiles, kind of a half smile. So concave up and increasing. So what changes at negative 2? Well, now it is concave down, but it still increases to negative 1. So can you change the concavity? So it's still going up. It increases, so it's still going up the whole time up to negative 1, but it goes from smiling to frowning. What happens after negative 1? Well, now it turns. So at negative 1, it has a maximum. So now it's going to decrease. But it continues to decrease with a frown. So this continues to frown and decrease all the way to 2. So it's decreasing, and this whole thing is a frown decreasing. So we have to follow both at the same time. It takes practice. And then when it's greater than 2, it's now going to increase, but it's going to increase concave down. So this is increasing with a frown. So it's still increasing, but it makes a frown. And notice at 2, we have a cusp. So the derivative doesn't exist at 2 because of that cusp. And then you follow it. So you go, okay, let's just start with increasing. So from all the way to negative 1, so from negative infinity to negative 1, this whole thing to negative, is it increasing? Then it decreases, and then it increases. Perfect. How about concavity? So all the way to negative 2. So right here is negative 2. So it's going to smile, and then it's going to frown to positive 2, and then it's going to continue to frown past 2. So it frowns and frowns. You can frown decreasing, or you can frown increasing. And then at 2, did it create a cusp so the derivative doesn't exist? All right, number 15. Number 15 says to use a calculator. So that's what I'm going to do. To determine if that function is concave up or down on the interval, including 0.523. So let's do this. With our calculator, oops, what did I do? So I'm going to clear this. Just give me a second. So I want the second derivative. Menu, calculus. I want the second derivative. Oops, that's not the one I wanted. So I wanted this one then. Press the button beside the number 9. And then move to this one will give you the second derivative. See the one with the 2? We want the second derivative. So let's do the second derivative. Oh, we also need to solve an equation. So let's just do that all at once. Menu, algebra, solve. We'll delete the first parentheses. There it is. So the variable is x. And then we're just going to type in the equation, which was 4x cubed plus sine 5x. And then I'm going to go comma x. See what this gives me. Oh, I didn't create an equation. That was my problem. So I'm going to make it equal to 0. My bad. And then let's see what answers it gives us. So when I make it equal to 0, I get negative 0.523 and positive 0.523. So those are my critical numbers for the second derivative. Oh, I could have also done that too. I'm going to do it a different way. Okay, but anyways, 0.523. Because 0.523 is what I'm looking at too. That's what it equals. Let me just back up for a second. So because I just want the second derivative, let's press the one beside the second derivative again. I made this mistake, add an x value. So let's press menu. Let's go to calculus and then derivative at a point. So let's press 2. Let me not make the mistake. The variable is x. The value is the x value is 0.523. And we're looking for the second derivative. So make sure you move it for that. And then type in 4x cubed. It's okay to make a mistake. See it, correct it, keep moving forward. Sine 5x. And then control enter. Now what I'm looking for is the answer positive or negative. So because you get the answer negative 0.012, so ignore this, the second derivative at 0.523 gives you the answer negative 0.01276, blah, blah, blah. So what I'm looking at is because when you plug into the second derivative, the answer is negative, that means concave down if it's negative. And the question was, use a calculator to determine the function is concave up or down. So we now, because the second derivative gives you a negative answer, we know that that number is in the middle of a concave down. So it actually wasn't too bad if I started correctly. 16. In number 16, find the absolute maximum and minimum for that function. So we have f at x equals x to the fourth minus 2x squared. And if I want to find the absolute max and absolute minimum from negative 2 to 1, I'm going to do a table. And I'm going to include the n values, which are negative 2 and 1. And then I need to take the derivative, first derivative, make it equal to 0, and solve it for any critical numbers I'm also going to add to it. So if I solve this, factor out a 4 and an x, I get x squared minus 1. So x squared subtract 1 is a difference of squares. So 4x gives you the answer 0. And then you have positive 1 and negative 1 from the other factors. So I already have positive 1. I need 0, negative 1. So between negative 2 and positive 1. So I already have positive 1. 0 is in the interval. and -1 is in my interval, so both of those numbers need to be added. Then I take each of those answers and plug them back into the function and see what the y coordinate is. So when I plug in -2, I get the answer 8. When I plug in +1, I get -1. 0 gives me 0, and -1 gives me -1. And now the question is, what's the absolute maximum and minimum? So the absolute max is 8. And the absolute minimum, it's okay, there's a tie, is -1, is the smallest value. Number 17. For number 17, it says find the c value guaranteed by the mean value theorem of that function. So f at x equals the square root of x minus 2 from 2 to 6. So is it continuous from 2 to 6? If I plug in 2, it's okay. 0 is okay. Plug in 6, it's continuous, and it's differentiable at that. So we're okay in terms of that. It passes the two conditions. I need to do the slope. So the slope is f at 6 minus f at 2 over 6 minus 2. The slope of the secant, or the average rate of change. This is the mean value theorem, where a rock equals I rock. So in this case, if you plug in 6, you get the square root of 4, which is 2. If you plug in 2, you get 0. So if I put this all together, I get 1/2. So you take the average rate of change and make it equal to the derivative of this. So recognize, to write this in calculus-friendly terms, would be to the 1/2. So the derivative would be 1/2 times 1 in front. Subtract 1 to the exponent. So 1 take away 2 is -1/2. And there's no chain here because the derivative of x, or no hook. The derivative of x is 1, so we don't need a hook. That's done. And that's what we're solving for. So if I want to solve this, the first thing I would do is divide both sides by half. That would be 1 equals this. The next thing I would do is raise both exponents to the -2. Now 1 to any exponent is 1. That's why I did that. Here, -2 and -1/2, they divide out and just leave you with x minus 2 to the +1. Add 2 and you get 3. The last thing you need to check about is 3 in my interval? Yes. So c equals 3 would satisfy the MVT, the mean value theorem. A rock equaling I rock, so the average rate of change equaling the derivative, solve for x, and you got it. Number 18. Almost there. You can take a break, if you need to. If the graph y equals ax cubed plus bx squared plus cx plus d has a point of inflection at 0, 2, and a relative maximum at -1, 4, find a, b, c, d. This is a substitution and system question. So first of all, they give you a point 0, 2. So 0 is x, 0, 0, 0, and y is 2. So what you're left with then, if you plug in y for 2 and 0 for x, is you already have one value. D is equal to 2. So I'm going to write this again, but this time with d equaling 2. Next, we have another point, -1 and 4. So 4 goes in, -1 goes in. This is before any calculus. And we get 4 is equal to -a, that's positive b, and that's -c. So far so good. We got 4 is equal to negative a plus b minus c. Oh, plus 2. Oops. All right, now we're going to take the derivative. So we're going to come back to this when we need to. So if I take the derivative here, and I'm going to take the derivative of this, that you got 3a x squared. You have 2 b x c for the derivative, and the derivative of 2 is 0. And then we take the relative max. So if I plug in -1 for x, the answer you're going to get is 0, not 4, because it's the derivative. So if you take the derivative and you plug in -1, it has to be a critical number if it gives you a relative max. So you plug -1 in, and it'll give you the answer 0. So let's simplify that. So now we have a second equation. What did I do? Oh, this is squared. So this should be positive 3a. So 3a minus 2b plus c. Now we're going to take the next derivative here. That's 6. So far we have this and we have this. So we're going to keep working. The next derivative would be 6ax plus 2b. That's it. The point of inflection, if I plug in 0, the answer should be 0, not 2. So if I plug in 0, it should give me the answer 0 as a critical number for a point of inflection for the second derivative. So if I plug in 0, I left with 2b equals 0. So now I know another one. b is equal to 0. So I'm going to come back here. So here, b is 0. So I'm left with 4 equals -a minus c plus 2. Let me clean that up. Subtract 2. So there. And then if b is 0, over here we have 3a plus c is what you're left with. Add these together. The c's eliminate. 2 is equal to positive 2a. Divide, and a is equal to 1. So we have a is equal to 1, b is 0. Yeah, let me summarize it here. A is 1, b is 0, d is 2. What variable is left that we don't know is c. So we come back and pick an equation with c in it. So I'm going to do this one with c in it. So I'm going to go 0 equals 3a, we know a is 1, minus 2b, we know b is 0, plus c. And then we solve it. So you get 0 equals 3 plus c, subtract, and you get all the answers. Let me just double check that I did it correctly. Looks good. I know it was a lot of work, but we did it together. I almost took up a whole page. I need another page. Here we go. Number 19. Sketch a smooth curve whose slope is always positive and whose slope is increasing. Now, if the slope is always positive, that's concave up. So for 19, something that's concave up and increasing. There you go. Smiling and increasing all the way. B, sketch something that's always positive. So if the slope is positive, it's concave up, but decreasing the other way. So, iota. Here we go. So it's decreasing, but smiling. There you go. So do you see the smile? And it decreases. Oh no, what is it? Whose slope is always positive and slope is decreasing. Let's start again. So when it says the slope is always positive, that means it's increasing. When it says the slope is decreasing, slope decreasing means concave down. So now let's try this again. So I want to increase but be concave down. So do you see the frown? There's an example of concave down but increasing. Part C, let me be a good reader. A curve whose slope is always negative. So the slope is negative, it is decreasing. Such a fancy way to say it's decreasing. The slope is increasing though. So if the slope is increasing, that means it's concave up. And can you draw a picture of something decreasing and concave up? So, decreasing but concave up with the smile. Last one, smooth whose slope is always negative. If a slope is negative, it is decreasing. And the slope is decreasing, which means it's concave down. So let's put this together. Decreasing and concave down. So it's decreasing but concave down. So this is decreasing and frowning. So look at each one. Decreasing and a frown. Decreasing and a smile. Increasing and a frown. Increasing and a smile. Just take some time to have this sense of concavity and increasing and decreasing and having a sense of what it should look like. Even I scratched out, try to be a good reader and thinker. Number 20. Number 20 says you're given x squared plus xy plus y equals negative 3. Find the derivative here. So that's 2x, the product rule. This is going to be implicit. So it's the first times the derivative of the second plus the second times the derivative of the first. The derivative of y is 1, but it needs a y prime, and the derivative of negative 3 is 0. So if it has a y prime in it, it stays on the left side. The 2x we're going to subtract. The y we're going to subtract. And then I'm going to divide out the y prime so I can then get y prime by itself. So y prime by itself is negative 2xy over x plus 1. And then it says find that derivative at 1, negative 2. So where there's an x, where there's a y, where there's an x, and then just solve it. So plug in positive 1 and negative 2. What is that? That's 0, right? Because the negative times the negative, that's negative 2 plus 2. Part B. Part B says find the second derivative there. So for the second derivative, I'm going to do the quotient rule. That's the bottom times the derivative of the top. That's negative 2, and the derivative of this would be y prime. Subtract the top times the derivative of the bottom, which is 1, and then the bottom squared. So again, I want to find the second derivative at negative 1, or at 1 and negative 2. So I'm going to plug some numbers in. So for x is 1. Y prime at that point, we just said the answer was 0. So we're going to plug 0 in for y prime. Y prime at that point, it's 0, so I can just plug in 0. So that's just negative 2 then. Minus negative 2 times 1. And then a negative and a negative 2. All over 1 plus 1 squared. So recognize the negative times the negative is positive. This whole thing is going to be 0 on the right. And then 2 times negative 2 is negative 4. And then 2 squared is positive 4. So I got negative 1. Yeah. So the second derivative at the point is negative. That means it's concave down at that point. And then the part C says, does that mean it's a minimum or maximum or neither at that point? So because of that, it's a relative max because it's concave down and it's a critical number. So because it gave me the answer 0 and the second derivative is negative, put it together, that means it's a maximum. All right, 21. At 21, you're given a number line, negative 3 and positive 5, and then answer these questions. So Actually, this goes to all the questions, not just 21 that follow. So 21, g at x equals f at x plus 2. Then the derivative at 4 is what? Less than or greater than 0. So the derivative here for this one would be the derivative here. The derivative of 2 is 0, so that's what's equal there. Then plug in 4. So the derivative is the same as the derivative here. So the derivative at 4 here is the answer positive or negative. So we say it's less than 0. 23, 22. So g at x equals negative 2 f at x. I'm going to take the derivative again for this one and then come back to the number line. So the derivative here would just be negative 2 f prime at x. So when I plug in 4 again, I get negative 2 and then 4. Now we just said that the derivative at 4 is negative. It's between negative 3 and 5. So if it's negative, you end up with a negative times a negative. And if you have a negative times a negative, then in this scenario, it's greater than 0 because the negative times the negative is positive. 23. So the derivative in this case is the derivative. Now, the derivative of x minus 10, we would have a hook here, but the derivative of this is 1, so there's no hook. And then when I plug in 4, when you plug 4 in here, 4 take away 10 is negative 6. So take the derivative where negative 6 is, what do you get? And you get a positive answer. So this last one, because you get a positive answer, it's greater than 0. All right, last question. You deserve it. Do you need a break? You want to finish this, don't you? 24. So that's a position function moving along a horizontal line. A, when is the velocity? So the velocity I'm going to take 3t squared minus 27. That's the derivative. When is the velocity increasing? So it's not when the velocity is positive, it's when the velocity is increasing, which means I need the second derivative. So to know when the velocity is increasing, I need the acceleration. That's the definition of acceleration, when velocity is increasing or decreasing. So I need the next one. That's 6t. Make it equal to 0. Solve it. So that's when the acceleration is 0, at 0. And then plug in. So if you plug in a negative number, it's negative into the acceleration. Plug in a positive number, it's positive. So you can tell from 0 to infinity, velocity is increasing. When is the speed increasing? Well, speed is the absolute value of velocity. So if I look at velocity, and I do the absolute value of it, I'm looking for when the signs are the same. So they could be increasing for the speed when the signs match. So I need to take 3t squared minus 27, make it equal to 0. I need to know when it's resting. So we're going to add 27. We're going to divide by 3. And then if I do this, take the square root, it's positive and negative 3. I'm going to do them right on top of each other. So this is acceleration and this is velocity. So at negative 3 and at positive 3. And I'll kind of try to match it up with the one below. Now, if I go back into here and I plug in a number smaller than negative 3, the answer is positive. Plug in like 0, the answer is negative. Plug in a number bigger than 3, the answer is positive again. So I have a velocity and acceleration. So for part B, I'm looking for where the signs match. So notice positive and negative don't match. But negative and negative match. So from 3 to 0, they match. Negative 3 to 0. So from negative 3 to 0, both acceleration and velocity are both negative. So when the signs match, the speed is increasing. Where else do the signs match? So after 3, it's positive and positive. So from negative 3 to 0 and 3 to infinity, we have signs that match and speed is increasing. Last question. When is the distance of the particle from the origin increasing? So the distance is increasing when the position and velocity share the same sign. So let me just do this lastly on a piece of paper here. So this is part C. I need to do this. I need to make it equal to 0. So I'm going to use my calculator just to solve it quick. Menu, algebra, solving. So if I do that, I get 5.950 negative. So I'm going to put that on a number line. So negative 5.950. I also have 2.306. And the last one, I got one more there. If I have to move the cursor over just a little bit, so highlight it and move it over, 3.644. So that is the position. So the question is, when is the distance of the particle from the origin increasing? So from the origin increasing, I'm also going to overlay it with the velocity. And I did that velocity, right? I'll do it again here. Negative 3 and positive 3 and 0. Or just negative 3 and positive. Yeah, just negative 3 and positive 3. And just looking at the last sheet. So at these times, it's at the origin. So if I plug in to here, any number smaller, like a huge negative number, it's going to be negative. If I plug in a number like 0, it's positive. If I plug in a number like 3 into here, it's going to be negative. If I plug in a huge number like a billion, it's going to be positive. So at these times, it's at the origin. And so it's left of the origin, right of the origin, left of the origin, right of the origin. And so I want to see when the signs match, because this tells me direction. So from negative infinity to negative 3, the signs don't match. But from negative 5.9 to negative 3, they're both positive. So negative 5.950 to negative 3, they both are positive, the velocity and the position. Then it stays positive, so they don't match. It becomes positive again after 3. So they're not matching. And then after 3, well, at 3 they're not matching, but at 3.644 to infinity, they both are positive. So where do the signs match for velocity and for position? From negative 5.950 to negative 3, they both are positive. From 3.644 to infinity, they both are positive. And there's no spot. Is there a spot I missed that both are negative? How about 2.3 to 3? Yeah, I missed one. So 2.306 to 3, from 2.306 to 3, they both are negative. So here's the signs match on that interval, right? That's a tier 1 billion question, right? Tier 1. Hey, we got to the end of it together. I appreciate it. We can look through it again if you want to. Mr. G Math over and out. Until next time.